On number 2, the residual plot and regression, you'll notice, is actually already both done for us. So whereas on number 1, we had to take all of the numbers, put it into the calculator, run the regression, get the residual plot. Here, this is already done for us. So the scenario is that we've actually maybe put all of our raw data into a computer program, and then the computer program has spit out the residual plot and some information for us. So really for us, the task is just to interpret what's happening here with this residual plot and what's happening with the information that's given to us. So there's some things that we've talked about up to this point in the semester. There's some things we have not. So what we need to focus on is just this little column right here where we have the constant and then we have the coefficient, right? So this represents our starting point. The constant represents our starting point, our y-intercept. And then the coefficient, this number here, is going to represent our slope, right, which we know is our rate of change. So they're going to ask us here in a second, interpret the slope, interpret the y-intercept, and so we should be able to do that. So let's talk about that, and we'll come back to A. So identify and interpret the value of the slope. So the value of the slope here is 233. Now 233 what? Well, the story here is there's an airline company that's interested in studying the number of commercial airplanes that has changed from the year 1990 to 1998. So an airline, we're assuming over this period of time, did they buy more planes or are there less planes? So we're trying to see the growth or decline of the airline. Well, so this is a positive number, this 233. So this would suggest growth, that the airline got larger. They got larger by how many? Well, 233, right? So what we can interpret that as is that for each year, the airline increased, and again increased because that number's positive, increased the number of planes by 233 approximately, right? Because we got that 233.517. So number of planes by, we'll say roughly, right? Because this is just an estimate, 233 aircraft. We'll say aircraft. Right. And so we always want to label, because we're not saying roughly 233 pizzas or roughly 233 BMWs. It's 233 aircraft, so we always want to label what it is we're referring to. Part C says, identify and interpret the value of the y-intercept. Okay, so what they mean by the y-intercept, again, is our starting point. What's our starting point? Well, we started collecting data in the year 1990, or at least that's what the problem tells us. So what we could say is that in 1990, the airline was operating 2,000, we'll say roughly, again because this is an estimate, so roughly 2,939 aircraft. So again, that's our starting point. So we're saying that this airline started off with almost 3,000 airplanes in their fleet, and then increased that by roughly a little over 200 each year. Right? Now, Part D, and again we'll come back to A. Part D says predict the number of aircraft flying in 1992. So what we're saying is, well, if they started off with roughly 2,900 in 1990, and we're adding over 200 a year, how much would be in 1992, 2 years later, right? Well, you could probably think if I had 200 to 2,900, I'm at 3,100, another 200, 3,300. That's an estimate, right? But so we actually want to know for sure what that is. So what we could do is actually plug this number in, predict the number of aircraft in 1992. That's 2 years after we started. So we're going to say that x is equal to 2, right? Because if 1990 is when x equals 0, 2 years later would be when x is equal to 2. All right, lunch cart workers. Thanks, Mr. Wolf. And so what we're going to do is take the equation. I haven't really written the equation yet, right? But let's take the information here. So really ends up being y equals your slope, 233 x, which would be number of years, plus where we started off at, 2,939, right? All right, so let's plug that in. So we're just going to take y equals 233 x, but in this case I'm going to plug in 2 plus, again, what we started off with. We're saying our airline started off with roughly 2,939 aircraft, and then what we're going to say here then is, what would that equal? So let's just throw that in the calculator. So we got 233 times 2 plus 2,939, and so we get 3,405, right? So 3,405 aircraft. Or we could also say planes, right? We just need to identify what it is we're talking about. So whether you said aircraft, planes, right? Same difference. All right, so now let's come back to A, right? So the question for A was saying, is this an appropriate model to use for the data, right? Because this is our model right here. This is our little crystal ball that we're using to make predictions. Maybe we were accurate, maybe we weren't so accurate, right? And that's why we will take a look at the residual plot to see how far off were we for each one of our predictions. Because again, the dot represents what actually happened, right? And then so we're measuring how far off were we for each one of our predictions. Well, the question is not assessing the quality of the linear model. It's just even asking, hey, should you even have used a linear model? Well, remember what we're looking for with the residual plot. There's a couple different things we can check. If we had the raw data, we could take a look at the scatter plot. We don't have that. Also, if we had the raw data, we could take a look at our r and r squared values, but we don't have that. So the only thing we're really going off here is our residual plot. And we know that with the residual plot, if there is a pattern, so let's say this. So we know that if there is a pattern, that it's non-linear. Could be exponential, could be any variety of different curves or functions, but we know that if you see a distinct pattern, that it's going to be nonlinear. Now, if it seems that it's randomly dispersed, then we could say that that is linear, right? So these dots, if you notice, they are randomly dispersed, right? Because it kind of, there's some above the line, some below the line, some are close, some are further. So there's no real distinguishable pattern. A residual plot that would say have a pattern might something look like this, where we could clearly see, let's say, something that's kind of parabolic like that. That would be a distinct pattern, right? So this would definitely be something that would be nonlinear. However, in our case, we've got a nice random dispersion, so we would say that, since the points are, since the values are randomly dispersed, right? Dispersed meaning kind of, spread out. Since they're randomly dispersed on the residual plot, then a linear model is appropriate. So it's as simple as that. Pattern and no pattern. No pattern suggests linear. And of course, certainly to make our case for that, we look at other measures. We look at the scatter plot. We look at our r and r squared values, but we don't have that here. So here, we're just going off the residual plot. All right, so go ahead and stop now and try number 2 on the right side.